The recent sections gave us the background that we now can look at the essential LTE radio procedures. As in every mobile communication system, also in LTE, a terminal needs to follow certain steps before it can receive or transmit data. Let's assume we do have an LTE capable terminal, as shown here. And guess what? The first thing we need to do is to power up the device. Right after powering up the device, the UE will start with the cell search and cell selection procedure, followed by derivation of system information and execution of the random access procedure. This procedure is summarized and known as LTE Initial Access. After the initial access procedure, the terminal is able to receive and transmit its user data. Before we now look at each of these steps separately, we need to talk about the physical signals and channels used in the downlink. LTE uses in the downlink two types of signals. Signals which are purely generated in the layer 1, the physical layer. These signals are the primary and secondary synchronization signal, as well as downlink reference signals. Further, LTE uses physical channels which derive the information data to be transported from higher layers, the layer 2 and layer 3. These are, for example, the physical broadcast channel, carrying essential system information, further several control channels, such as physical control format indicator channel, physical downlink control channel, which are required to inform the UE about scheduling decisions. The physical downlink share channel is used to transport the data, as we will see any kind of data. The obvious transport of user data to the device, but also system information or paging information. Back to the first step after powering up the UE. For the cell search and cell selection, just the downlink physical signals and the physical broadcast channel are important. A successful execution of the cell search and selection procedure, as well as acquiring initial system information, is essential for the UE before taking further steps in communicating with the network. As in wideband CDMA, LTE uses a hierarchical cell search procedure. The LTE radio cell is identified by a cell identity, which one is comparable to the scrambling code which is used to separate between base stations and cells in wideband CDMA. To avoid an expensive and complicated network planning, the number of physical layer cell identities is with 504 sufficiently large. To enable the usage of a hierarchical cell search, these identities are divided into 168 unique physical layer cell identity groups, where each group consists of 3 physical layer identities. A jingle to remember this principle is to think about first names and surnames. The most common English surname is, according to statistics, Smith, which would correspond to physical layer cell identity group number 0, for example. Align the physical layer identity now with the most common first names, for example James, John and Robert. These two types of information are now transmitted using two signals, primary and secondary synchronization signal, where the primary synchronization signal contains the physical layer identity, so the first name, and the secondary synchronization signal contains the physical layer cell identity group, which is, according to our jingle, the surname. Compared to real life, where you use your first name first when you introduce yourself, also the terminal looks first for the primary synchronization signal, then for the secondary one. The computing of the cell's identity based on a modulo 3 operation means multiplying the group identity with 3 and adding the physical layer identity. Let's look at the two signals now. The type of signal which is used for the primary synchronization signal is a Sadov-Chu sequence. Sadov-Chu sequences are Kazakh sequences, where Kazakh stands for constant amplitude, zero autocorrelation, where the name describes already the characteristic of those type of sequences. With a constant amplitude, a low peak to average power ratio is achieved, whereas zero autocorrelation means a good time domain behavior. When we look at the constellation diagram of the primary synchronization signal, recorded here with rohde and schwarz leading signal analyzer FSQ, we will get this result. Can we extract the characteristic of the primary synchronization signal? Yes, we can. The constant amplitude is indicated by the unit circle. The good autocorrelation can be observed by looking at each individual subcarrier carrying the primary synchronization signal. Subcarrier is a good keyword. In the frequency domain, the primary synchronization signal occupies 62 out of 72 reserved subcarriers around the unused DC subcarrier, which corresponds to the carrier frequency in the downlink. The remaining 10 subcarriers, 5 left-hand side and 5 right-hand side, are not used for any transmission. We can call them guard subcarrier. This helps to do match filtering, finding the right sequence used for the primary synchronization signal. As Christina explained, 72 subcarriers translate to 6 resource blocks, as 12 subcarriers are forming a resource block in the frequency domain. With 15 kHz subcarrier spacing, the occupied bandwidth around the carrier frequency is 1.08 MHz. By using the evaluation filter function coming with rohde and schwarz FSQ signal analyzer, you can look at each subcarrier individually. For the 3 different physical layer identities, 3 different set of choose sequences have been selected, which have shown the best behavior. The one displayed in the constellation diagram is the sequence for identity number 0. The already mentioned match filtering works generally in that way that the received signal is correlated with the possible sequences for the primary synchronization signal. This procedure is not executed on the received analog RF signal. In fact, this happens in the digital domain. With successful match filtering, the device has identified the used physical layer identity for this cell as well as 5 milliseconds timing. Afterwards, it can execute the next step, looking for the secondary synchronization signal and the physical layer cell identity group to compute the cell's identity. Looking at the constellation diagram showing now the secondary synchronization signal, we believe to see a pure BPSK modulation. In fact, the secondary synchronization signal is represented by an interleaf concatenation of 2 length 31 binary sequences. These 2 sequences are scrambled with a scrambling sequence depending on the physical layer identity, which is transmitted with the primary synchronization signal. So without finding the primary synchronization signal, the terminal cannot conclude on the secondary synchronization signal. The combination of the 2 used sequences defines the physical layer cell identity group. As the primary synchronization signal, the secondary synchronization signal also is transmitted on 62 out of 72 reserved subcarriers around the unused DC subcarrier. That is the frequency domain. So what about the time domain? When we look at the downlink frame structure explained by Christina beforehand, we can see that the synchronization signals are transmitted in the first subframe, subframe number 0, and in the 6th subframe, which is subframe number 5. So the repetition rate for the synchronization signals is 5 milliseconds. The 2 synchronization signals are always transmitted in the first time slot of that subframe, where the primary synchronization signal occupies the last OFDM symbol, and the secondary synchronization signal the symbol before. The determination of the cell's identity enables the UE to examine the pseudo-random sequence used to generate the cell-specific downlink reference signals, as the initialization of the generator based on the cell's identity and the used cyclic prefix, normal or extended. The information which type of cyclic prefix is used in that cell is derived here. The cell-specific reference signals do fulfill 3 tasks. They are used for initial acquisition, current demodulation and detection at the UE, as well as for channel quality measurement. To estimate the channel's quality and to help the eNode B to find a scheduling decision, the network informs the UE via system information about the power level with which one the downlink reference signals are transmitted. The UE is measuring that power level. The difference translates to a so-called channel quality indicator, a CQI value, which is reported back to the network. CQI value stands for a specific modulation scheme, QPSK, 16 QAM or 64 QAM, and which channel coding should be applied to the data. In that matter, the cell-specific downlink reference signal could be seen as a lighthouse, where the power level refers to the height of that lighthouse. In the matter of cell search, the reference signal helped the terminal to get frequency and time-wise fully synchronized. How that can be understood? Reference signals are transmitted as well-defined resource elements. A resource element is the smallest resource unit in LTE and translates to a subcarrier, respectively OFDM symbol. In the frequency domain, every sixth subcarrier carries a reference symbol out of the generated reference signal pattern. In the time domain, the spacing is 4 OFDM symbols as shown in the diagram. Thus, the resource block, which is 12 subcarriers, 7 OFDM symbols, when normal cyclic prefix is used, 6 OFDM symbols for extended cyclic prefix, contains 4 reference symbols at certain resource elements. LTE uses MIMO technology. 1, 2 or 4 antennas are used for transmission or reception. Depending on the MIMO mode, here spatial multiplexing, different data streams might be transmitted over the antennas. To ensure correct demodulation and decoding at the terminal site, the UE needs to distinguish between the different antennas. This is done with the help of the reference signals. As you can see in our example with the 2 antennas, the second antenna issues their reference signal pattern at other resource elements than the first antenna. The frequency and time domain spacing stays the same with 6 subcarriers and 4 OFDM symbols, but where the first antenna would issue their reference signal pattern, the second antenna would not transmit anything and vice versa. This is indicated by the hashed resource elements in the graph. With the help of the reference signals, the UE gets fully synchronized to the radio cell. After that, the UE looks for the physical broadcast channel, which carries the master information block. The physical broadcast channel is, as all control channel in Downlink, QPSK modulated. Prior to modulation, the channel is scrambled with a cell-specific scrambling sequence. In contrast to the synchronization signals, the physical broadcast channel is transmitted on the 72 subcarriers around the unused DC subcarrier. In the master information block, the UE finds the information which system bandwidth is used in the cell. 1.4, 3, 5, 10, 15 or 20 MHz. The system frame number, as well as the configuration of a specific downlink channel. Further, the UE gets the information how many transmission antennas are used in that cell. And this is all what the UE knows after successful execution of cell search and cell selection procedure. Further information are required to execute random access procedure and to enter the network. Let's see how system information are distributed in LTE.
Andreas, I have a question. You explained that the repetition rate for the synchronization signals is 5 milliseconds, so every 5th subframe. What about the physical broadcast channel?
Yeah, sure, good question. The physical broadcast channel and so the master information block has a transmission time interval of 40 milliseconds and can be found in every radio frame. But of course you need to decode the 40 milliseconds to get the whole information. The data in the master information block are the only system information which are transmitted via a dedicated control channel, means the physical broadcast channel. All other system information are transmitted using the shared channel principle. That is what Christina explained during explanation of channel mapping in LTE. At that stage we learned that the logical broadcast channel can be either mapped to the broadcast channel or the downlink shared channel as transport channel. The BCH is then mapped to the physical broadcast channel, where the downlink shared channel is mapped to the physical downlink shared channel. So all other system information than the master information block are mapped to the downlink shared channel, which is a fundamental difference to 3G mobile communication systems. Nevertheless, also in LTE, system information that logically belong to each other are summarized in system information blocks. Further system information blocks with the same timing requirement can be grouped into so-called system information messages. First of all, the UE needs to find scheduling information for those system information, which is provided by the system information block type 1. This one is already transmitted using the shared channel transmission principle and has a repetition rate of 80 milliseconds. With information out of the system information block type 1, the UE would be able to check the periodicity for system information messages. There could be up to 32 messages. A message contains system information blocks with the same scheduling requirements. The system information block type 2 is the one the UE is now looking for, as this one contains information about the common and shared channel usage and therefore information how to perform random access. System information block type 2 includes information about the random access channel, which is the transport channel, and the physical random access channel, which is the physical channel where the reg is mounted to. Timing is the one side of the medal. The other side, which resource blocks, so which part of the spectrum now carries the system information message, and therefore the system information block. We will later on talk a little bit more in detail about this, but as Christina already highlighted during explanation of the downlink frame structure, the first symbols of each subframe contains the physical downlink control channel, PDCCH, and this one informs all the UEs about scheduling decision, and beside this, on which resource block system information can be found. A specific identity is used on the PDCCH to address system information to the UE. This is the System Information Radio Network Temporary Identifier, which is defined by 3GPP, the standardization body, and is therefore known by all UEs. With decoding the right resource blocks, the UE received the information how to use the random access channel and how to access the physical random access channel and can perform the random access procedure. The random access procedure contains several steps. First of all, a knock-knock. The random access preamble is sent by the UE, which means, hello network, here I am. The preamble itself is a sort of choose sequence, which is sent on the physical random access channel. 6 adjacent resource blocks out of the available bandwidth are occupied by the preamble, but where these resource blocks are located is configured by higher layers via the system information. Based on information derived from system information block type 2, the UE also knows in which subframe a specific one or all in that radio frame the preamble can be transmitted and which preamble format to be used. At all there are 5 formats, where the first 4 are applicable for LTE FDD and LTE TDD, and the 5th one just for LTE TDD. The different formats are necessary to bridge the gap between the base station and the UE. After the UE has sent the preamble, it waits for a response from the network. If no response is received, the UE increases the power level with which one the preamble was sent. If the eNode B has received the random access preamble sent by the UE, the random access response comes on the physical downlink shared channel. This response includes uplink timing adjustments, instructions, an initial uplink resource grant required for transmission in step number 3, and an assignment of a temporary identity. In the next step, the step number 3, the UE first time uses the physical uplink shared channel. The transmitted information includes, for example, a radio resource control connection request, tracking area update, or scheduling request. It also includes the allocated identity. Step number 4 marks the contention resolution. The random access procedure can be verified using rohde and schwarz CMW 500 LTE protocol tester step by step or as a complete procedure. The instrument is ready, and so testing depends completely on the implementation status of the device under test. With passing the random access procedure, the UE is known by the network and would be able to transmit and or receive data. We know already that data in LTE, it doesn't matter if it is system or paging information, so control data or user data, is transmitted via the physical downlink shared channel. As the name implies, this channel is shared between all the UEs in the radio cell. And particular UE is interested to know if it is addressed with data and where to find this data. Another UE is looking for the radio resource blocks carrying system information, and so on. The device needs to be informed about the scheduling decisions, and therefore all devices need to read the physical downlink control channel. This channel is transmitted over the entire bandwidth in the beginning of each subframe. Via unique identities, information are provided to the UEs if they are addressed with data and where to look at on the physical downlink shared channel. But of course there might be more than one UE in a radio cell, and all of them needs to be addressed with control information once in a while. Therefore the amount of resources means how many OFDM symbols in the beginning of a subframe are occupied by the physical downlink control channel might differ. The UE needs to be informed about that. This information is provided to the UE by another channel, the so-called Physical Control Format Indicator channel. This channel, transmitted on defined resource elements on the first symbol of each subframe, contains the information how many OFDM symbols are used for the physical downlink control channel. Depending on the bandwidth used in this cell, the number of symbols differs. In case of a 10 MHz channel, respectively 50 resource blocks, at minimum 2 OFDM symbols are used in the beginning of each subframe, at maximum 3. 4 OFDM symbols are reserved for future use. The hybrid automatic repeat and request for LTE in the downlink works the same way as for HSDPA. The UE can request the retransmission of incorrect received data packets via ACNAC reporting. The ACNAC information is sent in the uplink on the physical uplink control channel, PUSCH, or the physical uplink shared channel, PUSCH. This depends if in parallel uplink data transmission is ongoing or not. The ACNAC sent in the uplink refers to the data packet received 4 subframes, means 4 milliseconds earlier in the downlink. This is a timing relation in LTE FDD. In TD-LTE it is a little bit different. Here the timing relation depends on the uplink downlink configuration, means how many subframes are allocated for downlink transmission, how many subframes are allocated for uplink transmission. Because of that, a single ACNAC response for providing HARC feedback could be used in TD-LTE for multiple PDCCH transmissions. As we learned, Evolved Packet System, EPS, is efficiently a connection-oriented transmission network, and as such, it requires the establishment of a virtual connection between the UE and core network, respectively Packet Data Network Gateway, before any traffic can be sent between the UE and the network. This virtual connection is called a EPS bearer, a term that emphasizes the fact that this virtual connection provides a bearer service, means a transport service with specific quality of service attributes. The EPS bearer corresponds to the PDP context used in GPRS wideband CDMA. The EPS bearer has to cross multiple interfaces to establish that connection. Between the UE and the eNode B, between the eNode B and the serving gateway via the S1 interface, and between the serving gateway and the packet gateway. A lot of procedures have to be executed and a lot of information are exchanged between network and the UE. As shown, tasks like the initial access procedure have to be passed first, further RRC connection establishment, attach request and PDN connectivity request, authentication and non-access stratum security procedure, checking the UE capabilities, access stratum security, RRC connection reconfiguration, attach accept default EPS bearer context request, and as a last step, the default EPS bearer context accept. So far the downlink and downlink related procedures. Let's look now at the uplink. As in a downlink, there are physical signals and physical channels. During explanation of the downlink HARC procedure, we already mentioned the 2 physical uplink channels, physical uplink shared channel and physical uplink control channel. The other channel in the uplink is the physical random access channel, which carries the random access preamble and which one we discussed during explanations for the initial access procedure. The 2 types of the physical signals are the demodulation reference signals, which are used by the eNode B for channel estimation and correct demodulation. Further, sounding reference signals used by the eNode B to find scheduling decisions based on the channel quality. As said, data are sent by the UE on the physical uplink shared channel. This channel, again as the name implies, is shared between all UEs in the radio cell. That means the UEs are sharing the bandwidth of, for example, 20 MHz equals 100 resource blocks when the radio cell is configured for that bandwidth. A UE would get resource blocks are assigned where QPSK, 16 QAM or 64 QAM can be used as modulation schemes. Note that 64 QAM is an optional modulation scheme in the uplink. The question is how different UEs are scheduled when they would like to transmit their data. The scheduling is made by the network, better the eNode B. On the physical downlink control channel, a specific format, the downlink control information format number 0, is used to indicate to a UE on which resource blocks to transmit its data and which modulation and coding scheme to be used. Further, this format indicates to the UE if frequency hopping should be used or not. In LTE, there are two modes of hopping: intra and inter-subframe hopping. Hopping at all is an optional feature, but it is an approach to overcome possible frequency selective fading on the radio channel. When intra-subframe hopping is configured, the UE hops from one resource block allocation to another one within one subframe. This means at the one slot the UE would transmit, for example, on the lower edge of the spectrum, in the second slot on the upper part of the available spectrum. Inter-subframe hopping means now that the UE changed the allocation from one subframe to another one. For each hopping mode, two types of hopping can be configured. Type 1 defines an explicit frequency offset used between the two allocations. This is shown in the screenshots taken from rohde and schwarz leading vector signal generator SMU200A. With the SMU200A, a 3GPP compliant uplink signal is generated and two fixed frequency offsets between the allocation are configured and shown in the two screens. Type 2 uses a predefined hopping pattern where the available bandwidth, for example 20 MHz corresponding to 100 resource blocks, is splitted into subbands and the UE hops between those subbands. To ensure proper demodulation, demodulation reference signals are used in the uplink. In contrast to the reference signals used in the downlink, the demodulation reference signals are not transmitted on specific resource elements. Instead, the demodulation reference signal is transmitted over the entire allocated bandwidth and occupies a specific single carrier FDMA symbol. The screenshot shows the timeplan of rohde and schwarz vector signal generator SMU200A, generating a 3GPP compliant uplink signal. 11 resource blocks are occupied and frequency hopping type 1 is applied to the signal. We can see that the single carrier FDMA symbol number 3 in the first slot and symbol number 10 in the second slot carries the demodulation reference signal. If the UE would be assigned to transmit on less or more resource blocks, the demodulation reference signal would also be transmitted over these resource blocks. This is mandatory due to the nature of single carrier FDMA. The other physical signal in the uplink are sounding reference signals. Sounding reference signals are used by the base station to estimate the quality of the uplink channel, to be used as a basis for scheduling decisions, means where a UE should transmit its data. The E-NUD-B is free in its decision to configure bandwidth occupied by the sounding reference signals, power level, etc. At this time, the UE knows where to transmit its data, which modulation and coding scheme to be used, if frequency hopping should be applied, and if there is a need to generate in addition sounding reference signals. Now it is important to know with which power level the UE should send its data. First of all, the UE calculates the power for the physical uplink shared channel based on this formula for every subframe, so every 1 millisecond. As it can be seen, the power level depends on various parameters, starting with the maximum allowed power, which depends on the power class. There is just one power class in LTE defined, defining plus 10 to 3 dBm as maximum power, which corresponds to the power class 3 in wideband CDMA. Next is that the number of resource blocks is important. A number of cell and UE specific parameters is taken into consideration, provided by higher layers, as well as the downlink path loss and the transport format. This information is derived within the DCI format number 0 on the physical downlink control channel, where also the transmit power control information is taken from. We looked here substitutional at the calculation of the power level for the physical uplink shared channel. The calculation for the physical uplink control channel, physical random access channel, and for the sounding reference signals based on similar formulas and is also influenced by higher layers and cell-specific parameters. With all the information we discussed on the last slides, the UE is now ready to transmit. The question is now when the UE starts with its transmission. The timing relation between receiving all the information via the DCI format number 0 on the physical downlink control channel and start of the transmission is 4 subframes, so 4 milliseconds. After 4 milliseconds, the UE starts transmission on a physical uplink shared channel on the assigned resource blocks with the calculated power level. In TD-LTE, the timing relation is impacted by the used uplink downlink configuration, and there is at least a 4 millisecond subframe interval between receiving the physical downlink control channel and starting transmission on the physical uplink shared channel in an uplink subframe. Of course, also the UE would like to know if the data it has transmitted has been decoded correctly by the eNodeB. To provide that feedback means sending ACNAC information, the eNodeB set up another downlink control channel. This channel is the physical hybrid ARQ indicator channel. This channel carries the ACNAC information to the UE. We already run into this channel as we discussed the information transmitted via the master information block. The master information block carries duration information for the PHIG. The duration of the PHIG differs for LTE FDD and TD-LTE. The PHIG is always transmitted in the first symbol of each subframe in the downlink. The ACNAC information on the PHIG corresponds to the data packet sent in the uplink 4 milliseconds before. Last but not least, we need to discuss the physical uplink control channel, PUSCH. The PUSCH carries the uplink control information, means a scheduling request, ACNAC information, CQI values, and parameters like precoding matrix indicator or rank indicator, which are necessary for MIMO transmission. A physical uplink control channel is only issued by the UE when no uplink data transmission is ongoing. In that case, the user data and uplink control information is multiplexed onto the physical uplink shared channel. That means one UE is only issuing a physical uplink shared channel or a physical uplink control channel, never both. The physical uplink control channel is transmitted on reserved frequency regions, means the lower and upper edge of the available spectrum. This minimizes the effect of possible frequency selective fading affecting the radio channel. Further, interslot hopping is used for the PUSCH. That means the transmission jumps from, for example, the lower edge of the available bandwidth to the upper edge within one subframe. This is also to ensure that the uplink control information arrives at the eNodeB. Depending on the information to be transmitted, different formats are used as shown in the table, using different modulation schemes and a different number of bits.
In this section we will have a closer look at the mobility procedures defined inside the LTE system. This means how the subscriber moves from one cell to another. This slide illustrates in a very simplified way the procedures for a handover from a UE between two base stations, a source eNodeB or base station and a target eNodeB or base station. Also the X2 interface between the two base stations is involved in this case. The mobility management entity is not changed. That means both base stations stay connected with the same mobility management entity or MME. So we have the case of an Intra-MME handover. The MME is part of the evolved packet core EPC in this figure. First of all, the UE is reporting measurements. This means neighbor cell measurements according to the measurement configuration provided by the base station. And the base station is then evaluating the measurement reports. The base station will decide about a handover in case, for example, a neighboring cell shows much better quality than the source cell. So this would be the handover decision. In case this neighboring cell belongs to another base station, we have an inter-base station handover, and the source base station will then communicate with the target via the X2 interface. The source will request a handover so that the target can do admission control and check whether it can accept the new terminal. In case it can accept the handover, it will send a handover request acknowledge message via the X2 interface. The target base station can then start the handover over the air interface. It is then sending the handover command to the UE, and in case of LTE, this is actually an RRC connection reconfiguration message. It contains all the required information regarding the target cell so that the UE is able to access the target cell. The UE can then detach from the source cell and synchronize to the target cell. And on the base station side, data packets, sequence number information can be forwarded from the source to the target base station again over the X2 interface, and the target can buffer the new packets. As soon as the UE is connected then to the target base station, the RRC connection reconfiguration procedure is complete. And the paths between the evolved packet core and the base stations can be switched so that the data path now goes to the new base station and all the new packets are delivered to the new target base station. So all the contacts, the UE contacts in the source base station can now be released, all buffers can be flushed, and all the resources can be released there. So there's not only intra-LTE mobility, but also LTE between 2G and 3G networks defined in the LTE. On this side, for example, the possible transitions between the LTE and GSM GPRS states, as well between LTE and wideband CDMA HSPA states are shown. In LTE there's only two protocol states defined on the radio resource control RRC level, the RRC connected and the RRC idle. These are shown in yellow here. And the mobility in RRC idle between LTE and the other technologies is done via cell reselection mechanisms. Mobility in RRC connected is done via handover procedures. For example, from the EUTRA RRC connected state to the UMTS cell DCH state, or from the EUTRA RRC connected state to either the GSM connected or the GPRS packet transferred mode state. In between LTE and GSM GPRS, you can see that also cell change order mechanisms, abbreviated CCO, are defined, also including network assisted cell change, NACC. Of course, not only transition from LTE to GSM-H and wideband CDMA HSPA, but also between LTE and CDMA 2000 based technologies is required. And this is true for both the HRPD high rate packet data and for 1xRTT circuit switched services. And this figure again shows the allowed state transitions in terms of state transition between RRC connected and the CDMA states and RRC idle and the CDMA states. Note that CDMA 2000 messages are sent transparently to the UE over the EUTRAN, and the base station and the MME acting as relay points. All the described mobility scenarios we have just seen for 2G, 3G, wideband CDMA, GSM and CDMA are part of 3GPP Release 8 specifications. So these interworking scenarios, mobility scenarios, they are all part of LTE from the beginning. Now the next section will cover MIMO multi-antenna technology. MIMO is a key feature of the LTE air interface because it is needed to achieve the high throughput and data rate requirements for LTE. MIMO stands for multiple input, multiple output, because multiple transmit antennas are used that form multiple inputs to the radio channel, and typically multiple receive antennas are used, which are provided with multiple outputs from the radio channel. So a brief introduction to MIMO in general before we go to the LTE specific things. We've seen that MIMO basically means using multiple antennas at both transmitter and receiver side, but what are you doing with these multiple antennas? What are the gains to exploit? First of all, a diversity gain can be exploited. This is illustrated in the first figure shown here. By transmitting the same data streams over multiple transmit antennas, for example at a base station site, the receiver, which could be the wireless terminal, has multiple replicas of the same signal available. And so at the receiver side you can achieve a higher signal to noise ratio. This diversity gain is very efficient to combat fading over the mobile radio channel. However, the data rate cannot be increased because each antenna is actually transmitting the same information stream. You have actually more redundancy available. Note that typically the streams transmitted by each antenna are coded with an additional antenna-specific pattern to further increase the diversity effect. An example would be the space-time or space-frequency coding according to LMUTI. That is a very commonly used scheme. The next figure shows a slight difference, and it shows a simplified example for spatial multiplexing. And in this case, a multiplexing gain can be exploited by using the multiple antennas. And now each transmit antenna transmits a different data stream, S1, S2, and so on as shown here. And these streams are transmitted simultaneously over the same radio resources over the air interface. And this is possible by exploiting the spatial dimension. So by doing so, the data rate can of course be increased because now more data is actually transmitted over the resources at a certain point in time. However, of course, no diversity gain can be exploited. The transmission may not always be successful, and this really largely depends on the correlation characteristics of the mobile radio channel. If the channels that are formed between the transmit and receive antennas are highly correlated, then the performance of spatial multiplexing will deteriorate. So spatial multiplexing really works best in uncorrelated scenarios. And we really have a high dependency of the performance depending on the channel conditions, which is also the reason why spatial multiplexing typically is being tested in fading scenarios, and fading simulation is a very important testing feature for testing MIMO systems. In fact, it is also possible to switch between the MIMO modes, transmit diversity and spatial multiplexing, and this is also done in LTE. The decision which MIMO mode to apply is taken in the base station based on the UE feedback received. So MIMO is typically operated as a closed loop scheme using this UE feedback loop. Now, not to forget a third possibility of using multiple antennas. In the case of beamforming, an antenna array with closely spaced antenna elements is used to focus the energy in the direction of the terminal, and ideally also to null out interferers. This is achieved by adapting the amplitude and gains of each antenna element to form the beam. Beamforming is also supported in LTE, and it is especially beneficial for TD-LTE, the TDD mode, because of the reciprocity of uplink and downlink channels in TDD operation. This means that the uplink transmission from the mobile can be evaluated by the base station, and the necessary adaptations on the beam pattern in the downlink can be derived from this uplink transmission. Now this slide summarizes the MIMO modes used in the LTE downlink before we go in more detail on some of them. Transmit diversity is one MIMO mode. It is using a space frequency block coding scheme, SFBC, and that is used as an additional antenna coding. As explained on the slide before, the transmit diversity mode is increasing the robustness of the transmission, but not the data rate. So the space frequency block coding scheme will also be further explained in the following to give you an impression of what's really done there with the signal. Achieving the high data rates in LTE is possible by using the spatial multiplexing MIMO mode. Again, this allows transmission of different data streams simultaneously over multiple spatial layers. And to further improve the performance of this MIMO mode, a so-called codebook-based precoding approach is applied. That means the signal is pre-coded before transmission in an appropriate way. And this will be illustrated further in the following as well. There's an open loop mode and a closed loop mode available for this spatial multiplexing scheme. The closed loop mode is relying on UE feedback, and the open loop mode is beneficial at high mobile speeds where the UE feedback may not be reliable anyway. So then the base station can operate in open loop mode. An additional scheme used in LTE is called cyclic delay diversity. It is used in addition to spatial multiplexing as a further enhancement. An antenna-specific delay is added to the signal transmitted by each antenna, delaying the signal effectively, and this is done by a cyclic shift of the signal on each antenna. And this effectively results in an artificial multipath situation experienced at the receiver side, causing increased frequency diversity effect. Finally, beamforming can also be applied in LTE as well, which is especially relevant for the TD-LTE part. This picture illustrates the LTE downlink transmitter chain inside the base station. It shows the processing that is done for each code word that is output from the channel coding stage and what happens to it until the transmission over the antenna ports at the right-hand side. So what is a code word? A code word is basically corresponding to a transport block. The transport blocks pass down from MAC layer to the for transmission over the physical layer. And the code word is an entity that has been channel coded by the turbocoder. In LTE, you can actually have two code words in parallel that can independently be channel coded and then transmitted in parallel in case of the spatial multiplexing scheme. After scrambling and modulation of the code words, the MIMO layer mapping and precoding takes place. And that is the stage where it's actually decided whether transmit diversity or spatial multiplexing is applied, and which would result then in a different mapping and precoding operation specific to each MIMO mode. And also a wide range of configuration option exists at this stage. You have different precoding types depending on the radio channel characteristics, for example. Then the resulting signal out of the MIMO precoder is mapped on the OFDM time frequency resources for transmission on each antenna port. And again, LTE supports up to 4 transmit antennas at the base stations. Could also be 2, for example, depending on whether it's 2x2 or 4x2 or 4x4 MIMO. So now to better understand this layer mapping and precoding stage from the slide before, let's have a closer look on what happens in case of transmit diversity. So what is really done in these stages there of the signal processing. And the example shown here is for a 2 transmit antenna case. And it shows the space frequency block coding. So in case of transmit diversity, only one code word can be transmitted at once because we do not have spatial multiplexing. And the figure illustrates what happens to 2 symbols, D0 and D1, of that code word. First of all, these symbols are split onto 2 different layers in the layer mapper, and they are then precoded according to the space frequency block coding scheme, which is predefined in the standards. So the example shown here shows that the symbols are duplicated and then the conjugate complex signals, or even the negative ones, are transmitted according to a predefined rule. The resource element mapper defines how to transmit these symbols in time and frequency and over the antennas, and it's shown here that the same information is transmitted actually on both antennas because we have transmit diversity, but with different precoding. So antenna 1 in this example, TX1, transmits the symbol D0 at a certain subcarriers. At the same time, the antenna 2 transmits the symbol D1 on this subcarrier, with a special coding applied for this symbol. And looking at this other subcarrier, it's vice versa. TX2 transmits D0 and TX1 transmits D1. So actually we transmit a redundancy of information, but we achieve an increased robustness, but no increase in throughput or data rate compared to the single antenna case. So this is transmit diversity. Now let's have a look at the downlink spatial multiplexing operation in LTE, which again uses a codebook based precoding. So what is a codebook? The codebook is actually for the 2x2 MIMO case shown here on the left hand side, this table taken from the specification. The table effectively contains entries of precoding vectors and matrices, which are multiplied with the signal in the precoding stage of the base station. So now the selection which of these matrices or vectors to take, which codebook entry to select, is taken in the base station, and the decision is based on the regularly received UE feedback that the UE is providing. So the UE is of course estimating the radio channel and also evaluating the quality of the received signal, and based on that the UE recommends the optimum precoding matrix out of the codebook. The codebook is known of course at the base station and the UE side. And this feedback is called precoding matrix indicator, PMI, so the UE is actually pointing to one of these entries. And how is that done? So the UE is actually evaluating which precoding matrix would maximize the reception quality. Besides the PMI, the UE also reports CQI feedback, channel quality indication, and also a rank indication RI, which provides information on the rank of the channel matrix. So that information will provide the base station with input whether spatial multiplexing or transmit diversity should be used. So this is downlink spatial multiplexing based on the codebook based precoding as the other possible MIMO mode, and the base station has now the different configuration options available here. Finally, we look at the LTE uplink. There's no single user spatial multiplexing defined for the LTE uplink as we have seen for the downlink, and this is caused by the fact that the UE is not supposed to have two full RF transmit chains. But still the UE may have two transmit antennas and can switch the RF path between either one of them to exploit the diversity effect due to that. So the base station provides feedback to the UE which transmit antenna to use, and this is a closed loop scheme as well, so the scheme is optional for the UE to support. That's important to note, not all UEs have to support this. Another scheme used in the uplink is the so-called multi-user MIMO or collaborative MIMO, supported in LTE, so two UEs actually transmit simultaneously over the same time frequency resources that is indicated in this small picture, and the UEs are actually scheduled by the base station, so the base station needs to decide whether this is actually possible or not, and each UE just needs to have one transmit antenna in this case, as it's also indicated in this picture. But you can imagine that this scheme only works in certain radio conditions, so it's really up to the base station to evaluate that carefully. Multi-user MIMO enhances the capacity, as you can imagine, because you exploit the radio resource twice by sending different UEs over these radio resources, and the users share the same radio resources. So the base station has to distinguish the users again, and that is done by different reference signals that are assigned for the different UEs.